Hello, my name is Nidhi Koppikar and I will be presenting the research paper Designing and Implementing Malicious Hardware as part of the course System and Software Security, instructed by Professor Matthew Hicks. Here is a brief overview of the presentation. We'll start with understanding the background for the paper, that is, hardware trojans. This will include its components and properties. Followed by this, we'll be taking a look at the historical context of the paper. Then, we will look at the problem statement, salient contributions of the paper, and an overview of the hardware design and tools and technologies used. After that, we'll assess the strengths and flaws of the paper. Then finally, we'll look at the future scope of the study and then conclude the presentation. The paper discusses the design and implementation of Illinois malicious processors to explore complex attacks that could occur in the hardware Trojan space. Before diving into the paper, it is important to understand the fundamental concept of hardware Trojans, which will help us give a background to the concepts we will be discussing in the paper. So, what is hardware Trojan? What it involves is the malicious modification of an IC chip circuits. It's usually done when creating or designing the chips, basically in the manufacturing space. So in essence, it is a piece of hardware that is concealed inside a bigger piece of hardware. What happens is it awakens at random intervals and engages in malicious behavior that is also unpredictable from the user's perspective. So as they are present inside the hardware, they cannot be detected using something like an antivirus software. The way it is usually identified is by observing the physical appearance of the device or by its behavior. The main components of the hardware Trojan are trigger and payload. The trigger decides when the hardware Trojan will wake up, and the payload decides what will happen when the Trojan is woken up. So, a typical Trojan would wait for a specific trigger, and once it occurs, a specific payload will be executed. The payload can modify the functionality of the device, and then the triggers can be something like an input from a user from a specific address bus. What a payload could potentially do is something malicious like leaking secret information to unauthorized individuals or organizations. Here are few properties of the hardware Trojan. It can be put before or after manufacturing. It can be inserted by some intellectual competitor. It can be extremely small in size. It is stealthy and nearly impossible to detect. It causes IC to malfunction in field. Here is an example of hardware Trojan. This is a crypto device analogous to an integrated circuit. In this IC, we have a crypto module and a secret key stored within the IC. So how it works is, it takes an input, uses the key, feeds the two in the crypto module. The module then performs an encryption which produces a ciphertext. So with the key kept a secret, the ciphertext won't get the input directly or without permission. But then, if a developer puts an additional hardware or Trojan, as we see on the right side of the slide, this additional hardware acts as a multiplexer with the trigger acting as a select line. So if the trigger is sent to it, the input data that was earlier restricted can now be accessed. Let's take a look at the historical context for this paper. A recent Department of Defense report focused on a few trends that contributed to the threat of inserting hardware Trojans in ICs or integrated systems. The first one was the dependence on commercial suppliers for high performance ICs, which otherwise is not feasible economically. The second trend is the globalization of supply chain of the IC industry, due to which different operations like design, manufacturing, and testing happen in different countries, giving it a scope for infiltration of Trojans. A prominent case happened in the year 2006, where iPods shipped by Apple were infected with Ravmon-E virus. Another case was during the Cold War, where CIA sabotaged the oil pipeline control software, which was then allowed purposely to be stolen by Russian spies. A few recent cases were also observed, where Trojan-infected external hard drives were sold by Seagate in Taiwan. Due to this, personal data of users was compromised. As there is a lower level of control to check the hardware, it makes it easier for the hardware Trojan to go undetected. Attackers obviously have a basic advantage over software-based attacks when they use modified hardware. Attackers are more likely to be able to evade detection and prevention due to the reduced level of control available. The latest Subvert project demonstrates how to take control of the operating system using virtual machine monitors. Due to the attacker's access over the entire software stack above, defending against an attack becomes much more challenging. Since the hardware is the only layer present, such an attack has a fundamental advantage over the defense. Even while the security community has made some initial progress on this issue, we still know very little about malicious circuits. There was a study conducted by IBM to solve this issue. So IBM created a Trojan circuit. They make the encryption key leak by selectively turning off parts of an encryption circuit. This by far is the finest hardware attack implementation we are aware of. However, it is not without flaws. The first one being their attack directly targets hardware level abstractions. They expose higher level abstractions and system level elements, while also leaking encryption keys from an encryption circuit. So, other than this, there isn't much work done on malicious circuit design space. This paper thus addresses a few of the shortcomings. Now, let's take a look at the contributions of this paper. By designing the Illinois malicious processors, the capability of powerful attacks using little circuitry is addressed. The first contribution is that the circuit designed goes beyond just an attack on the hardware, but also considers mechanisms to support general attacks. Two mechanisms, memory access and shadow mode, are designed, which we'll understand in later slides. The second contribution is that potential attacks are also tested using the circuits designed. Like with memory access, privilege escalation attack is implemented. For evaluation, IMPs are tested both on hardware as well as simulation. Malicious hardware has become a major worry for computer security due to our escalating reliance on computer systems and also the expertise of our adversaries. Malicious hardware can be used in a number of ways to undermine the security of computer systems, such as stealing confidential data, modifying or corrupting data, or interfering with system performance. Malicious hardware design and implementation are difficult tasks, but the results of such an assault could be disastrous. Given these concerns, the authors aim to address the following problem. How can malicious hardware be designed and implemented? And what are the potential consequences of such attacks for computer security? The authors seek to provide a comprehensive discussion of the technical aspects of malicious hardware, including the challenges involved in its design and implementation, as well as the potential consequences of such attacks, and then also the difficulties in detecting and mitigating their impact. Through their research, the authors aim to provide valuable insights into this important and rapidly evolving area of computer security. So, in a nutshell, the problem statement is that the paper focuses on the addition of Trojan circuits to existing hardware to carry out attacks. In this study, analog and discrete perturbations are also considered. Now, let's take a look at the hardware designs. The mechanisms designed in this study are memory access and shadow mode. Memory access provides the attacker the ability to surpass the memory management unit and access the memory. The shadow mode, on the other hand, allows the attacker to perform invisible malicious firmware. How the memory access attack works is, a malicious software initiates a memory access attack by pushing a series of bytes onto the data bus to enable memory access circuits. Once the sequence has been noticed, the MMU in the data cache disregards the CPU privilege levels for memory access and grants unprivileged application access to all memory, including the internal memory of the operating system. It is basically like using a magic value to access all memory of a device. The shadow mode lies between pure hardware and pure software. This mechanism avoids use of additional hardware, but rather uses existing circuits in the device and provides them invisible instructions. Also, this attack goes beyond the IMP, where instructions can be stored in cache and data cache lines, avoiding detection. Now that we know a bit about the attacking mechanisms, let's look into the types of attacks that can be executed with these mechanisms. Starting with privilege escalation. This type of attack is performed using the memory access mechanism. In this attack, the malicious service grants root privilege level access to the attacker. This attack uses simple hardware mechanisms to give the malicious software system access. The next type of malicious service is login backdoor. This attack uses the shadow mode mechanism. In this, the attacker sends an unsolicited network packet to the target system, after which the target system OS inspects the packet. In the process of inspection, the Trojan is triggered and the contents of packet are considered new firmware, and it loads in the target system's processor. After dropping the unwanted packet, the target operating system resumes normal function while being unaware of the assault. Now, the login application is monitored by the shadow mode firmware. The malicious service updates the return result of the password checking function to return true when it notices a user attempting to log in with the password "let me in," enabling access to any user who uses this password. Basically, this is an example of how they have tested the shadow mode firmware in their paper. So now, there are two advantages to this. The first one being it is flexible. The attack can be updated through the network itself, giving the attacker an advantage to cope with changing software environments. Then the second advantage is it keeps the system from acquiring additional states and events that are visible to users outside of the CPU. Now coming to the final malicious service on this slide, stealing passwords. This attack also uses shadow mode mechanism. The primary difficulty in this attack is that finding the password in loads of random data. In order to identify processes that are likely to receive passwords, the service initially intervenes on the write library call and looks for the string password. It then intervenes on the subsequent read call to note probable passwords. Here is a list of the tools used in this study. A modified Leon 3 processor was used in the FPGA environment. The operating system used here was Linux. Other cable and equipments used were the Ethernet, USB, and the VGA. Let's take a look at a few strengths of the paper. First is novelty. The design and implementation of malicious hardware is a new and significant topic in computer security that is covered in this paper. The writer's contribution is extremely noteworthy because they were among the first to tackle this subject. Next, the technical depth. The technical features of malicious hardware, including the difficulties in designing and implementing it, are thoroughly discussed by the writers. Additionally, they discuss the possible effects of malicious hardware as well as the challenges involved in identifying and minimizing its effects on computer systems. The relevance. As more devices are connected to the internet and as attacker sophistication rises, the subject of malicious hardware is becoming more and more important. For scholars and practitioners interested in computer security, the paper is a great resource because it offers insightful information on the subject. While the paper does provide a lot of useful insights, there are also a few flaws that can be worked on, like the limited scope. The paper does not go into great length about mitigation tactics or other potential solutions, focusing primarily on the design and deployment of malicious hardware. Then there is a lack of practical examples. The writers describe the technical aspects of malicious hardware in great detail, but they do not offer many real-world examples or case studies. Because of this, it could be challenging for readers to comprehend the ramifications of the ideas discussed in the paper. Now it is outdated as well. Since the paper's 2008 publication, a lot has changed in the world of computer security. Some of the precise details in the article may no longer be accurate or appropriate, even though the concepts covered therein are still relevant. Malicious hardware is still a pertinent and significant subject of study. Here are some details about the paper's potential future. Here are a few ways in which it can be extended. First is the mitigation strategies. More studies require to identify effective mitigation techniques given the growing threat posed by rogue technology. This could entail the creation of fresh methods for identifying and lessening the effects of malicious hardware, as well as the investigation of other hardware models that are more impervious to malicious attacks. The second way it can be extended is advancements in hardware security. New potential for reducing the dangers caused by malicious hardware may arise as a result of developments in hardware security, such as safe enclaves, trusted execution environments, and hardware-based security features. Additional study in this field may aid in identifying and combating fresh dangers, as well as inventing fresh remedies that can enhance the safety of computer systems. Another way the study can be extended is with the help of emerging hardware technologies. The emergence of new hardware innovations like quantum computing and the Internet of Things or IoT may bring with them both new potential as well as the difficulties in the field of harmful hardware. Research in this field could be useful in identifying and specific security threats that these new technologies represent and in creating solutions that are efficient in reducing those risks. In conclusion, the paper Designing and Implementing Malicious Hardware offers insightful information about the development of malicious hardware and the repercussions for computer security. The authors investigate the difficulties involved in the design and execution of malicious hardware and provide a thorough overview of its technical features. They also emphasize the significance of taking security considerations into account when building computer hardware and systems. The work has a number of advantages, including its uniqueness, relevance, and depth of technical knowledge. The article does, however, have certain flaws, such as its narrow focus, dearth of real world examples, and it being outdated. Despite these drawbacks, the study of malicious hardware is still relevant and crucial, and the paper lays a solid groundwork for future investigation in the field. The study stresses the significance of taking security considerations into account when developing computer systems and hardware, and offers useful insights into the development and use of malicious hardware. As new hardware technologies are developed and the subject of computer security continues to advance, its future scope is still very important. These are the references used for the presentation. Thank you very much for your attention. For more details, I would encourage you to go ahead and read the paper Designing and Implementing Malicious Hardware.